Hello everyone and welcome back to FatalSec. In this video, we are going to discuss logical shifts as well as logical rotations. And these two instructions are really important as they allow us to manipulate numbers at a bit level by shifting everything to the left or to the right. And it has a lot of unique and interesting properties that are actually really useful to take advantage of. In order to better understand these operations, we will represent everything in binary. That way you will be able to see what's happening at bit level. Okay, so these are the instructions which we are going to explore today. First four instructions are for performing shift operation and the last two instructions are for performing rotations. And each instruction can be accessed in two ways, that is either using a constant or immediate value directly as its operand or using a register as its operand. Okay, so let's start off with shifts. There are two types of shift operation available, logical shift left and logical shift right. First, let's understand the concept of logical shift left by considering a number, let's say 24. And let's first understand the concept of logical shift left by considering a number, let's say 24. Over here, I am not representing the whole 64 bits, so I have truncated all other bits, and for now, we are considering only 8 bits. So in 8 bits, we can represent 24 in binary as 000110000, right? Now, when we perform logical shift left, what we have to do is to move all the bits one by one to the left from the least significant bit, that is from bit 0. Currently at 0th position we have 0 bit, right? So this 0 will be moved to the left by 1. So now at first position we have the 0 which was there at the 0th position, and at the 0th position that will be padded with 0 by default. Then at the first bit we have again 0, so this 0 will now then be moved to second position. Then again we have 0 at the second bit, so this will be then moved to the third position, and then we have 1 at the third position, right? This will be now moved to the fourth position and so on. So in the end we will get 00110000, which is 48 in decimal, right? So if we perform logical shift left on 24, we will get 48. One important point to note here is that number obtained after shifting one bit is actually double the original number. So initially we had 24, and after performing the shift operation we now have 48, which is indeed twice the value of 24. So what we can conclude from this is that logical shift to the left is a faster way to perform multiplication by 2. So this is one of the reasons why we do logical shift left. Let's now quickly see the syntax of this logical shift left instruction in ARM developer's guide to understand how we can use it while programming. Okay, currently we are looking at logical shift left immediate. So according to the syntax, this logical shift left instruction basically takes three operands. First one is the destination register, second one is the source register, and the third one is actually a constant or immediate value which will tell this logical shift instruction by how much amount shift has to be performed. You already know the naming conventions by now. W we will use if we want to access 32-bit version of the registers, otherwise we will use X representation of the registers, right? Now let's program it in ARM assembly. So over here, let me create a new assembly file called lsl logical shift left.s. Firstly, we have to declare a global symbol using dot global declarative followed by the label start. This start will act as an entry point for the program from where it starts executing, right? Then we are going to declare a new section called dot text, which is going to contain all the assembly instructions. So inside this section, we have to define this start label. Now over here, firstly, I'm going to use a move instruction to initiate the source register, which is required by the logical shift left instructions. So for the source register, I'm going to use x1 register, and the value which we saw in previous example, that is 24, right? Now let's use logical shift left instruction, and the first operand it takes is the destination register. So let's say we want to store the result in x0 register. Okay, then the source register, so source register we have just initialized, that is x1, and then the third operand is going to be the constant value by which we want to perform the shift. So over here I am just going to use 1, and then finally let me paste the exit routine. This routine basically tells the operating system to exit the program normally. So that's pretty much it. Let's save this assembly file and assemble it using ARC64 Linux GNU assembler. This takes this lsl.s as the first input, and then it will generate lsl.o, which is an intermediate object representation. This is not the final executable. And we did not get any error, which means there is no error in our assembly code. All right, let's see. So over here we have our .o file. Now in order to generate final executable, we have to make use of another tool called ARC Linux GNU loader. Okay, this will link all the required dependencies which are required by this program and generate a final executable for us. So this will take this object file as the input, and it will generate the final executable with the name lsl. Enter ls, and there we have our final executable. Now obviously we have not printed out anything on the console, so even if you try to run it directly, you won't see anything. However, it is performing the logical shift left operation on 24/1. So in order to see that in action, let's make use of GDB and load this executable inside it. Okay, so our executable is loaded now. We can see the disassembly of start function using disassemble command. So this is exactly what we have programmed, right? Move followed by logical shift left and then the exit routine. So in order to analyze what's happening at each instruction, let's simply put a breakpoint at the very first instruction using break, and then the offset where our instruction is this address. So let's copy this and paste it over here, hit enter. So now our breakpoint is set at this particular offset. Now we can start the execution by typing run command, enter. And now you can see in our debugger that the program counter is currently pointing to the very first instruction of our program, which is move x1 comma x18, which is nothing but 24 in decimal. And initially all the registers are initialized with 0. Now let's see what happens when we execute it. So let's step over it using step I command. So the first instruction is now executed. Program counter is moved to the next instruction and it's waiting over here, which means x1 is now containing hex 18. Let's see. Yes, x1 is now containing hex 18. Let's execute this logical shift left instruction now. Step I, enter. So this instruction is now executed, and according to this, after performing logical shift left by 1 on x1 register, the result will be stored into x0 register. So in x0 we should have the resultant value. Let's see. Yes, x0 register is modified and now it's containing hex 30, which is nothing but 48 in decimal, right? So that's how logical shift left operation works. Let me quit this terminal and clear out the console. Let's now quickly see another variant of logical shift left instruction, that is using register instead of immediate value for shift amount. So the behavior or the output is going to be the same as what we have seen just now. And let me just show you the difference between the syntax of these two variations of logical shift left instruction. Okay, so you can see that now we are looking at logical shift left register variation, and the syntax is pretty much the same. This also takes 3 operands. The only difference is in the last operand. So first operand is the same just like the previous one, which is the destination register. Second operand is the source register, and the third operand is now a general purpose register instead of having a constant value for shift amount. So the shift amount, which will tell the instruction how many shifts to perform, that value needs to be stored in this register first. Okay. Alright, so let me quickly copy the existing program which we have created, lsl.s, to another file called lsl.r.s, where r stands for register. Enter. I am going to modify this one instead of creating a new from scratch, just to save some time. So what changes we have to do over here? First is we have to make use of another move instruction which will contain the amount of shift we need to perform. So for that I'm going to use x2 register, and shift amount is going to be 1, right? And then we have to make a slight modification in the lsl instruction. So first operand is as usual the destination register, second operand is the source register, and now instead of this immediate value we have to put x2 register, okay, which is containing our shift amount, and x1 register is basically containing the value on which shift has to be performed. Okay, let's save this and compile this program again using ARC Linux GNU assembler. This time the file name is lslr.s and it is going to generate lslr.object file. There we go. Now we have to make use of linker to finally generate the executable with the name lslr, and there we have our executable. Now to see it in action again, let's make use of gdb and load it up like this. Let's quickly see the disassembly of start label. We have introduced a new move instruction, and in the lsl instruction the third operand is now a register. Okay, let's set up a breakpoint at the very first instruction, which is present at this offset. So let's copy and paste it, enter. Now the breakpoint is set at this particular offset, and let's tell the debugger now to start execution using run command. So the debugger is stopped and the program counter is pointing to the very first instruction, that is move x1 comma hex 18. So we already know what's going to happen. 18 value will be stored into x1 register. Let's quickly step over it and see the value in x1 register. Yes, we have hex 18. And the program counter is now pointing to the next instruction, and according to this instruction hex 1 will be stored into x2 register, right? So let's step over it and see the value in x2 register. Yes, it's modified and now containing hex 1. All right, now coming on to the next instruction, which is lsl x0 comma x1 comma x2. According to this instruction, whatever the value present in x2 register, that will be used as the shift amount. So in x2 we have 1, so it will perform logical shift left by 1 on the value stored in x1 register, which is hex 18, that is 24 in decimal, right? So let's see what do we get now. We have executed and the result should have stored into x0 register. Let's see. So x0 register is now modified and it's containing hex 30, which means x0 is now containing 48. So that's how you can use both the variations of the instructions. Either you can use the shift amount directly as a constant value, or you can store it in a register first and then use it in your logical shift left instruction. That's pretty much it about logical shift left instruction. Let's quit this and clear out the terminal. Let's move on to the next instruction, which is logical shift right. Let's first understand the concept of logical shift right by considering the same number 24, and in 8 bits we can represent it in binary like this: 0001100. Now when we perform logical shift right, what we have to do is to move all the bits one by one to the right from the least significant bit, that is starting from 0. So the very first bit which is present at 0th position will be moved out and it will be eliminated. We don't have to bother about this bit anymore. And at this place we now get the bit which is there at first position, that is 0. Similarly, at the first position, now we will get the bit which is there at second position, right? Then at the second position, we will get the bit which is there at third position, which is 1, and so on. So in the end, we will have 0000110, which is 12 in decimal, right? Now, you can guess what happened over here. In logical shift left, the number is actually getting multiplied by 2. Whereas in logical shift right, the number is getting divided by 2. So we can conclude from this that logical shift to the right is a faster way to perform division. So this is one of the reasons why we do logical shift right operations. Let's now quickly see the syntax of logical shift right instruction in ARM developers guide to understand how we can use it while programming. Firstly, we are looking at logical shift right immediate mode. Okay, so as per the syntax, again logical shift right instruction takes 3 arguments, very much similar to what we saw in logical shift left immediate version. First operand is the destination register, second operand is the source register, and the third operand is going to be the immediate or constant value, which represents the amount of shift needs to be performed. Not to mention again that the blue register representation we use when we want to access 32-bit version of the register, otherwise we will use X representation of the registers, right? So let's program it in assembly, going back to the terminal, and this time let me create a new file called logical shift right. And firstly we have to declare a global symbol using .global declarative followed by the label name, let's say _start. You know now what the significance of this .global start symbol. This will act as an entry point for the program. Then we are going to declare a new section called .text section, which is going to contain all the assembly instructions. So inside this, we can define our start label. So in order to perform logical shift right, we first have to initialize the source register. For that, I'm going to make use of move instruction, and I'm going to use x1 as my one of the source registers, and the value on which we want to perform logical shift right is 24, right? Then next instruction is going to be none other than logical shift right, and this takes first operand, which is the destination register. So let's store the result in x0 register, followed by the source register, which we have just defined, x1, right? Then finally the immediate value, which will tell the instruction by how much amount shift needs to be performed. In this case, let's just shift it by 1. Okay, and finally let me paste in the exit routine, which will tell the operating system to exit or terminate the program normally. That's it. Let's save the program now. Let's use ARC64 Linux GNU assembler to assemble it, and this will generate a output file lsr.o, which is an intermediate object file, not the final executable. So now we have lsr.o as our object file, and in order to generate the final executable, let me use the linker tool, which takes this object file as an input and finally generate lsr as our final executable. There we go. Now to see it in action, let's load it inside GDB as usual, like this. So this lslr executable is now loaded in our debugger. Just to be sure, let's see the disassembly of the start label. So this is exactly what we have programmed, right? And in order to analyze each instructions one by one, let's set up a breakpoint at the very first instruction, which is present at this offset. So to set up a breakpoint, we have to use break command followed by the offset, enter. So now the breakpoint is set at the very first instruction, and now we can simply tell the debugger to start executing the program using run command, enter. And as soon as the first instruction hit, the debugger is stopped. Before executing this instruction, let me show you. Currently all the registers are containing 0, right? So after executing this instruction, x1 register will be having hex 18. So let's step over this instruction using step I command, and now in the x1 register we have hex 18. Then the next instruction which is going to be executed now is the lsr instruction, logical shift right, and according to this, whatever the value present in the x1 register, on that it will perform logical shift right operation by 1, and the result will be stored into x0 register. So let's step over this instruction and see what do we get in x0 register. X0 register is now containing hex C, which is nothing but 12 in decimal, right? So like I explained you earlier, logical shift right operation basically divides the number by 2. Alright, let's quit this and clear out the terminal. Let's now talk about another variant of logical shift right instruction, which is instead of using immediate value for shift amount, we can also use register, which will contain the value of shift. So the behavior or the output is going to be the same as what we have seen just now. And let me also show you the syntax for that in ARM developers guide. So currently we are looking at logical shift right register variation, and the syntax is pretty much the same as what we saw for logical shift left register mode, right? It takes 3 operands. The only difference is in the last operand. Instead of immediate or constant value, we now use a general purpose register, which will tell the instruction by what amount shift needs to be performed. Then the first operand is as usual the destination register, and the second is the source register. Alright, going back to the terminal, let me quickly copy our existing program which we wrote for logical shift right, which is lsr.s, and put it into a new file called lsr, where this extra r denotes register mode. Okay, so instead of creating a new program from scratch, I am just copying existing one and doing the modifications. Let's open this up over here. To make it compatible with register mode, what we have to do is we have to use another move instruction to initialize the shift amount. As usual, the shift we want to do is by 1, so let's put 1. And now in the logical shift right instruction, we just need to change the last operand. Instead of the constant value, now we will put x2 register, which is containing the shift amount. So that's pretty much it. It's now using register for the shift amount instead of the constant value. Let's save this program and compile it using ARC Linux GNU assembler. This is going to generate an object file, and then finally we have to use linker on this generated object file in order to get the final executable with the name lsrr. Okay, ls, there we go, we now have this lsrr executable. Let's see it in action. So loading it up again using gdb lsrr, which is the name of our executable. And let's quickly see the disassembly of the start label to make sure that this is the right program. And yes, this is the new move instruction which we have introduced, and in the logical shift right instruction you can see the third operand is now a register. Let's set up a breakpoint at the very first instruction to analyze it instruction by instruction. Enter. Breakpoint is now set at the very first instruction, and let's start the execution using run command. Because the inputs are the same, the output is again going to be the same. Let's just make sure that the program is working as expected. So according to the first instruction, x18 is going to be stored into x1 register. Let's step over it using step I command and observe what we have in x1. Yes, it's containing hex 18. Then the next instruction is going to store hex 1 into x2 register, right? So let's step over it again and see what do we get in x2 register. X2 register is now containing hex 1, and then finally we are at the logical shift right instruction. So according to this, the value present in the x2 register will be used as the shift amount. So in x2 we have hex 1, so it will perform logical shift right by 1. This is the source register x1, which is containing hex 18. So on hex 18 it will perform logical shift right by 1. So let's quickly step over it using step I and see the result in x0 register. So in x0 we have hex C, which is nothing but 12 in decimal, right? This is the expected output. So just like logical shift lefts, you can use logical shift right either by directly providing the shift amount as an immediate value, or by storing that shift amount into a register first and then use that register as a third argument for logical shift right instruction. Okay, let's quit this debugger and clear out the terminal. Okay, so that's all about the shift operations. Let's now come to the rotations. Rotations are quite similar to shift operations with one key difference. In rotations, the bits that are shifted out from one end are reintroduced at the opposite end. Especially in a right rotation, the least significant bit is moved to the most significant bit, and the remaining bits are shifted accordingly by one position. Let me explain this to you with an example. So again, considering a number, let's say 25 this time, we can represent 25 in 8-bit register like this: 000110001. Let's perform rotate right operation on this. So what happens is the bit present at the 0th position, which is the least significant bit, will be shifted back to the 7th position. Earlier in logical shift left or right operations, what we were doing is we were simply eliminating this bit, but now instead of elimination we are moving it back to the register, the most significant bit. So the bit at the 0th position, which is 1 in this case, will be moved to this 7th position, and then the rest of the bits will be shifted by 1. So the bit present at first position, which is 0 bit, will be moved to the 0th position. Similarly, the bit present at second position, which is again 0 bit, will be moved to the first position. Then the bit present at third position, which is this 1, will be moved to the second position, and so on. So finally we will get 10001100 as the result. Let's now quickly see the syntax of this ROR instruction in ARM developers guide to understand how we can use it while programming. Okay, so over here we have the official ARM developers guide on ROR immediate. So as per the syntax of this ROR instruction, it also takes 3 operands. First one is the destination register. Then the second one is the source register, which is going to contain the value on which we will perform rotation. Okay. And then finally the third operand, which is a constant or the immediate value, which will tell the instruction amount by which shift needs to be performed. Nothing fancy, pretty much the same syntax. So let's program it in assembly by going back to the terminal and create a new program called ror.s this time. And as usual, firstly we need to declare a global declarative followed by the start label. Then we are going to declare a new section called .text section, which is going to contain all the assembly instructions. So over here we can define the start label. And according to ROR syntax, we first have to initialize a source register, right? So for that, let's use move instruction. I'm going to use x1 register as the source register and the value which I have just explained during the example, which is 25. Then the instruction itself, ROR, the first operand it takes is the destination register. So I'm going to use x0 as the destination register, followed by the source register, which is x1, which I have just defined over here. And then is the rotation amount. So for this example, I'm going to rotate it by 1 only. Okay. And then finally pasting the exit routine to simply terminate the program normally. Save the program now and assemble it using ARC Linux GNU assembler. Takes ror.s as the input file and it will generate ror.o as the intermediate object representation. Then we need to use the loader to finally generate our executable with the name ROR. There we go. You know what we have to do next. Load it up in GDB like this. See the disassembly, start label. There you go. And let's put a breakpoint at the very first instruction, which is present at this offset using break command. So now the breakpoint is set at the very first instruction, and let's start execution using run command. So according to the first instruction, x19 will be stored into x1 register, right? Let's step over it and see what do we have. x1 is now modified and containing hex 19 as expected, right? Then coming to the ROR instruction. According to this, the value present in x1 register, which is hex 19, this will be rotated by 1. See by stepping over this instruction, and according to this the result has to be stored into x0 register, right? Let's see what do we have in x0 register. We do get something, and this hex value is coming out to be so big. It's because, like I explained, the first bit, which is 1, that is moved all the way back to the most significant bit. Okay, so one thing to note is that there is no ROL operation. We only have ROR, and it is also not used very much by the developers. You will mostly find this operation in crypto based libraries where hashing needs to be performed or any other cryptographic operation needs to be executed. Okay, that's it for this lesson. Let me know in the comment section whether this ARM assembly series is useful or not. And in the next video, we are going to see how we can actually write if else loop in ARM assembly. So stay tuned for that.